Hi guys, welcome back to our channel. So today we'll be studying about the electrical properties, right? So we know that there are mainly, in case of solids, there are mainly three kinds of solids depending upon the conduction of electricity, that the conductors, insulators and semiconductors. So what are these and what are these ranges? Actually, in case of solid, we can see the conductivity of electricity. Matlab, it means that how much electricity a solid can conduct will depend on these units, right? And how these units are proliferated, these are extracted from whatever we can say that different kind of doping, different kind of electronic arrangements and electronic configurations that helps to release the different electrons in or outside a particular orbit. So let's move on. Now we can see the conductivity range. First of all, we will see the conductivity range. A solid has a conductivity range of around 10 to the power minus 20 to 10 to the power 7 ohm inverse meter inverse, right? So in this particular case, sigma, we consider it as the conductivity, right? So conductivity is also the reciprocal of how much it's conducting, how much resistance or specific resistivity it has, right? So let's carry on. First of all, we'll write these things, that conductors have a range of conductivity of 10 to the power 7, 4 to 10 to the power 7. This has the most highest electrical conductivity or capability of carrying electrons or free electrons. Then insulators, it will have a range of 10 to the power minus 20 to 10 to the power minus 10 ohm inverse and meter inverse. Then semiconductors, it will have a range of 10 to the power minus 6 to 10 to the power 4 ohm. Now look at this. In these semiconductors lies between these two. Okay, I mean to say insulators, conductors and insulators. Here lies the semiconductors according to the range. Now look at that range. It starts from here, but semiconductor ends in here, right? That's why we have divided these three conductivity portions. Let's see how the conductivity works. Suppose we have an atom and this one is the outermost electron, right? In certain way, either it may be either naturally or by heating up or by due to the different kind of defects we have studied earlier, uh, the electrons will be released after gaining certain amount of energy, right? So what would happen, these electrons will generate a free electron flow. How? Suppose in this case there are 6 different atoms arranged in this particular case. Now if this one loses one electron, this one will lose one electron, this one, this one, this one and this one, all of these lose one electron, then it will pose 6 electrons in these particular regions. So these electrons will lie in these interstitial spaces and they will be considered as the free electrons. So these electrons will be known as the free electrons. These free electrons will help to conduct the electricity. What happens afterwards? Suppose the this is a solid, right? The free electron will come to the surface and will flow in a particular direction. So this is the flow of free electron, and in the opposite direction the vacant positive positions will run. So in this way the current will flow, and in this way the electrons will start to flow. That's how a particular solid or electron can transfer a particular amount of electricity. That's how a conductivity of a solid is gained. Now let's see what are the different kinds of conduction bands and how these conductions works. Okay. Now what happens that if we draw a line, suppose our electron was in here, and then this is another band, this is an energy level E1, E2, and this is energy level E1. So whenever it gains some amount of energy, what would it do? It will jump in the next orbit, and then it will come back to the first orbit when it will release the energy, right? Release energy. And we know that E2 minus E1, that energy in case of light becomes h nu according to the Einstein's theory, right? Then suppose this one is the normal band and this one is the conduction band. So there's a gap between these two bands, right? What kind of bands, what kind of gaps? Then we will watch it. Now let's understand how these bands work actually. In this case, that there is a overlapping metal section in the first one, and then in the second one we can have insulator, then in third one we have the semiconductors, right? So in case of first one, there is a overlapping section between them, between the empty band and the filled band. Means this portion contains certain number of electrons in here, and this portion do not have any kind of electron, or their energy is literally empty. In these sections we can also find the same thing, but if this particular section contains a overlapping section, it will pose certain amount of electricity. And in case of semiconductors like silicon and germanium, we can have that in this particular section there is a small energy gap, hence the electrons can jump from here to here, but due to large energy gap, electrons will not be able to jump from the filled band to the empty band, hence it will not be able to conduct the electricity, hence these will be called the insulators. The energy bands in case of insulators remain really high at distance, but in case of metals they will contain certain overlapping section, and in case of semiconductor they will have a small energy gap between them. Now in case of a perfect crystal, we can have these kind of structures. In this perfect crystal system, we will have these spiral lines shows that there is certain continuity among these, right? So in this particular structure we can see that every one in this particular section they have a tetravalent. These are they have a particular tetravalent structure, means these have a tetravalency, right? So what happens if I move one electron from here? Then it will create an imbalance in this particular section. These kind of imbalances basically results in from heating up the molecule or heating up a particular kind of solid, and or by inserting or doping by astatine or maybe a boron infusion in them, right? Now what kind of changes will be there? In case of semiconductors, we can make a semiconductor a particular conductor, because by transforming or pushing one extra electron, suppose this one was a case where now it can accept one electron, right? Now from outside I am introducing another electron, but it will bring one more extra electron in this particular section. So what would happen? The normal structure of the tetravalency will be diseased, right? Then these particular structures on the next one we can see that they will result in a n-type or p-type doping. Let's see about the doping. Now let's move to doping. Suppose this was what? This was our original structure, right? Now if I am introducing another electron, where will it locate itself? In this interstitial space, this interstitial space, right? In this particular interstitial space, if we introduce one extra electron, then this extra electron will act as a free electron. This one will act as a free electron and will move on the surface of that particular metal. So this kind of, whenever suppose we are introducing As in here, what we'll have? We will have a particular As electron which is extra. This one is the extra electron. This extra electron will help to conduct the electricity in this case. Now this kind of doping is known as n-type doping. What happens? In this case, suppose we are having a pentavalent metal, right? Suppose in this particular case, these are silicon or germanium, right? Now what happens if we introduce, यहाँ पे जो silicon था, these are silicon, right? Now these silicon, all of these silicons are tetravalent. They are having a valency of 4. Then at the outermost shell they will have 4 electrons. This one, this one, this one, and this one. 4 electrons. But if we introduce As, in this case, they will have, As has, actually in case of As, we can have a pentavalency. So there are 5 electrons in this case. What would happen if I introduce in this section? Then we will get one extra electron. this one extra electron will help us to conduct electricity. Now, in this case, in what is the case of p-type electron? Now, what we know, this is 4, right? If we have introduced that, or if we introduce 5, then we will get one extra electron. But what happens if I introduce, this is n-type. Now let's move for the p-type conduction. Now in this particular case, suppose in case of silicon, silicon is tetravalent, but I have introduced boron, a trivalent compound, a trivalent element, right? So in this particular trivalent element, if we introduce boron, then this silicon will be replaced. But boron in here, boron has max to max 3 electrons at its outermost shell. Then what would happen? It will create a vacant position and lack 1 electron, because it has 3 electrons surrounding it, right? So this type of conduction will be this type of semiconductor will result in a p-type doping. What happens? I am repeating again. Suppose this was silicon. So 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons were there. But if I introduced boron in this particular section, what would happen? A electron in this particular section will decrease. So this type of doping will be known as the p-type doping. Okay. So this will help us to carry the electricity from one particular stretch of atomic solid state structure to the next one.